Good morning, everyone. My name is Manuel Ochoa. I'm from Purdue University, and I'm here to talk about an inexpensive impact sensing platform for spinal cord injury experiments. So first I'll talk about a little bit about spinal cord injuries and how they're being studied. Then I'll talk about the platform itself, what tests we've looked at, and what we're planning to do after that. So spinal cord injuries. A spinal cord injury is a very devastating condition that imposes physical, psychological, and financial burdens on the patient, not just the patient, but also their families and society as a whole. Its occurrence rate is estimated at about 40 new cases per million people per year, and that's just in the United States. And most of these are due to occupational hazards or sport injuries, automobile accidents, military combat. In all these cases, of course, the type of injury that occurs is going to differ. Type of injuries ranging from either transection or concussion or compression, and also depending on what part of the spinal cord is injured, that will determine the severity of the injury. But in all cases, it greatly reduces the quality of life for the patient, and there is no effective therapy. So the patient has to rely on assistive technologies and a lifetime of rehabilitation. Part of the reason for the lack of effective therapies is that there is a poor understanding of the underlying mechanisms of spinal cord injuries. So we don't really understand how tissue damage is correlated with damage at the cellular level or at the protein level. We can look at the spinal cord and see that it's a complex structure. It has it looks different along the transverse plane as well as the longitudinal plane. We can see that it's also a multi-level system where we're looking at tissue, we're looking at cells, we can look at the proteins that are attaching to the cells themselves. And all of these play an important role with spinal cord injuries, but it's difficult to understand exactly what's going on, and it requires a lot of research. So most of this research has been done using in vivo or ex vivo experiments in combination with modeling. In vivo experiments allow us to use a rat or a guinea pig model and actually see directly how a spinal cord injury affects. However, that requires complicated surgeries and then post-surgery animal care. And in the end, we're limited as to how much we can probe the animal for electrical signals or chemical signals. A better approach, at least one that gives us more information now, would be to use ex vivo experiments. And in that case, we can take a segment of the spinal cord of the rat or the guinea pig, put it on a platform, and expose it to electrical signals, mechanical signals, and at the same time we can measure the applied loads, any deformations, and any electrical characteristics of it. And then we can take that and apply simulations and models in order to take what we see on the boundary, essentially, on the boundary of the spinal cord, and try to get some information of what's going on inside. It's still a complicated process, but the translation neuroscience laboratory at Purdue has been working on some of these tests. And here's one example, one test setup that has been used. On this side we see a pressure load that's being applied to a spinal cord sample. You can see the segment of the spinal cord here in figure C. And this test, basically, it allows for low frequency pressures or static pressures while allowing for electrical recordings. Now, if we're interested in mechanical recordings, that has also been done more recently. And here we see a test setup. In this case, a spinal cord segment is placed again in a custom platform, and then the spinal cord is exposed to a pressure wave. So this is in this case, it's a blast wave generator. Then when the pressure wave hits the spinal cord, there are pressure sensors in the same region that detect the pressure in real time. And there's also a 90,000 frames per second camera that looks at the deformations of the spinal cord. After that, there's a lot of image processing in order to get deformations of the spinal cord in relation to applied pressures. And we can see that this setup ends up being expensive. I mean, we're talking about a really high-speed camera and sensors that are pressure sensors that are about $1,000 each. They're also pretty bulky when we compare them to the spinal cord. This is about maybe 1 centimeter. The spinal cord samples that we're using are about the same length. So it's bulky, and we can't put a bunch of them together along the length of the spinal cord. It would be useful to have some inexpensive platform that allows us to sense strain, strength, or sense impact along the length of the spinal cord. So that's what we wanted to do with this. We're going to make an inexpensive platform that we can use to sense what's happening along the spinal cord. And for this, we would need something that's flexible, something that can move along with the spinal cord, something that's small so that we can put more than one sensor, preferably, along the length of the cord, and something that's inexpensive and that we can readily machine so that it's available to anyone who's interested in using it. Well, we can use an array of cantilevers that are made of a piezoelectric material. In particular, polyvinyl fluoride, PVDF, can be used as this array of sensors. It's an electromechanical transducer. It can be purchased in sheets. It can be coated with metal. You can purchase it already pre-coated with metal to make connections easily. And best of all, we can machine it mechanically. And of course, it's low cost. So we can use this in a platform like what we see here. Straightforward approach. We have a chamber where we can place the spinal cord. The chamber can be made of any appropriate polymer. Polymers are good to keep costs down. And we see here cantilevers of PVDF on the side. We can have them arranged on the side, on the bottom, on the top, however we want them. In this case, they're positioned in that direction to be able to sense longitudinal waves. They could be positioned in other angles to sense transverse waves or a combination of both. PVDF sheets are thin. You can buy them easily at 28 micron, 52 micron, 100 micron thickness. So we can put a bunch of them together to have a high density sensing along the length of the spinal cord. And this platform allows us to gather data electrically in real time without having to do post-processing, image processing after gathering data. The fabrication of this platform is pretty straightforward. We might use tools that are accessible to everyone. One of these is laser machining, which is becoming more popular now, along with other rapid prototyping technologies. And another one is this cutter plotter that we see here. The laser machining can be used to make the acrylic chamber, the main part of the chamber. It does heat up the material at the points where we're cutting, but that's okay for the acrylic. It allows us resolutions down to about 25 micron. So we can use it for making slits for the PVDF. The PVDF, that one's usually tricky to work with, especially with traditional cleanroom technology, because it's very sensitive to temperature and other processing techniques. But we can process it mechanically by using the cutter plotter. We can see a cutter plotter basically takes a blade, runs it along the material, and traces out a computer-generated design to cut out the strips. So in this case, we can take the strips, mask them with a tape, passivate them with Parylene, so that we can later use them in the spinal cord without having them short out. And finally, where's my cursor? Finally, remove the tape, make the electrical connections, and assemble the device. we can see that the machining of the PVDF is very good. We get sharp corners. The edges are not ragged. They're very smooth. And these are some of the properties of the PVDF that we were using. We worked with a couple different lengths, 6 millimeters, 11 millimeters. Thickness, we kept that constant for now. And we see resonant frequencies of about, first resonant of 247 hertz. And that's good. That's about the frequency range that we saw later in testing. So here's an example of one particular platform. Again, we can change the number of strips that we have in there, change the orientation. We wanted to characterize the PVDF, see how well it worked in comparison to other pressure sensors and other data that has all previously been gathered. So we used agarose gel 0.5% as a model for the spinal cord, dropped weights, and measured the pressure at one end while measuring the voltage output from our sensor on the other end. Pressure wave was around between 100 and 200 hertz, so we can expect the PVDF to be able to follow. And we do have a voltage output versus pressure plot here. We can see a positive trend, 38 millivolts per kilopascal. And the sensor is suitable for low pressures, 10 or less than 10 kPa. You can see that if we put the PVDF on different regions of the spinal cord or different distances from the point of impact, we see a change in the amplitude. That's what we see in this figure here. So we can detect how the pressure changes at different locations. And later we'll be looking at, we did some preliminary tests with blast impact. The correlation dies down, especially after 100 kPa, but we're working on changing the dimensions of the PVDF and also testing actual spinal cord samples to see if we can detect blast measurements also. In this case, the blast wave is too fast so that PVDF can't follow. You can see that it doesn't have any resonances at really high frequencies. So we have this low-cost platform that can be modified, can be easily machined, and it's accessible to everyone. And compared to commercial sensors, this is a lot lower cost, and it can be used for measuring or sensing impact in spinal cord samples. So I'd like to thank NSF, Berkeley Technology Center, and everyone in my group. And I guess if there are any questions, I'll take any questions.
Before we do the next presentation,